As we move into the case study component of the density, zoning, and resilience module, our focus shifts from conceptual frameworks and regulatory tools to real-world applications. Throughout this module, we have examined how density patterns, land use regulation, and zoning mechanisms influence urban resilience by shaping exposure to climate risks, guiding spatial structure, and integrating ecological processes into the built environment. The case studies presented here illustrate how these principles are operationalized in different global contexts. Each example demonstrates how regulatory approaches, institutional arrangements, and spatial planning decisions interact to produce resilient outcomes. This lecture begins by outlining the learning objectives and then examines a series of international case studies that illustrate different approaches to urban density and risk mitigation. The presentation explores Rotterdam as an example of Delta City adaptation, focusing on water-sensitive planning and climate resilience. It then discusses Singapore's performance-based green urbanism, highlighting the integration of environmental design and high-density development. The lecture also reviews New York City's post-Hurricane Sandy adaptive zoning strategies, which demonstrate how planning regulations can respond to extreme events. Finally, Tokyo is presented as a case of earthquake-resilient high-density urban design, emphasizing how dense cities can be made safer through strong building codes, spatial planning, and advanced monitoring systems. This lecture aims to help students understand how climate-responsive zoning principles are applied in real-world planning contexts through internationally recognized case studies. It examines the spatial, regulatory, and governance mechanisms that support adaptive and resilient zoning practices and compares different zoning models across diverse geographic, climatic, and institutional settings. The lecture also evaluates the effectiveness of zoning tools in addressing challenges such as flood risk, heat stress, biodiversity, and social equity. Finally, it seeks to extract transferable lessons and key success factors that can inform future zoning reforms and planning practice. Rotterdam's success in climate-responsive planning begins with an extraordinary level of vulnerability. The city sits in one of Europe's lowest delta regions, with most districts located several meters below sea level and directly exposed to storm surges from the North Sea. At the same time, it receives high volumes of river discharge from the Rhine and Meuse, creating a combined threat of coastal, fluvial, and pluvial flooding. These risks are further intensified by climate change, which increases sea level rise, extreme rainfall, and urban heat accumulation across Rotterdam's dense industrial and residential areas. Rotterdam provides one of the most sophisticated global examples of climate-responsive zoning in a highly vulnerable delta environment. Rather than viewing water as a threat to be resisted, the city has redefined it as an essential structuring element of urban form. This paradigm shift is reflected in zoning codes that integrate flood risk assessments, hydrological data, and adaptive design standards into the very foundation of land use decision-making. Tools such as climate-adaptive waterfront zoning and multifunctional water plazas demonstrate how zoning can guide development patterns while simultaneously enhancing ecological performance and public space quality. These interventions support resilient districts that are capable of absorbing, storing, and redirecting water during extreme rainfall or storm surge events. An important dimension of Rotterdam's approach is the way climate-responsive zoning is embedded within long-term spatial planning and investment cycles. Adaptive zoning measures are not applied as isolated or exceptional responses, but are systematically integrated into redevelopment projects, infrastructure upgrades, and public space interventions across the city. This allows climate adaptation to be implemented incrementally through routine urban transformation, reducing costs and increasing feasibility. Continuous monitoring, scenario testing, and collaboration with academic institutions further enable Rotterdam to refine its strategies as climate projections evolve. In this sense, the city's experience demonstrates that resilience is not a fixed outcome but an ongoing planning process, sustained through institutional capacity, regulatory flexibility, and a shared understanding of water as a defining element of urban life. Beyond its technical achievements, Rotterdam's model is rooted in strong institutional collaboration between municipal authorities, regional water boards, and research institutions. This governance framework ensures continuous learning and long-term adaptation. As a result, Rotterdam stands as a leading international example of how spatial flexibility, integrated infrastructure, and adaptive zoning can collectively strengthen both urban resilience and social livability. The Benthamplain Water Plaza is one of Rotterdam's most iconic examples of multifunctional climate-adaptive design. Developed by De Urbanisten, the plaza illustrates how public space can simultaneously serve recreational, ecological, and infrastructural purposes. During dry weather, Benthamplain functions as a lively urban square, providing areas for sports, seating, and community activities. However, during periods of heavy rainfall, the entire space transforms into a temporary water retention basin, capturing runoff from the surrounding neighborhood and relieving pressure on the city's drainage system. What makes this project globally significant is its integration of hydrological engineering with everyday urban life. Instead of hiding stormwater infrastructure underground, the design celebrates water as a visible, educational, and engaging element of the city. The stepped basins, permeable surfaces, and interconnected channels demonstrate how climate-resilient interventions can be embedded aesthetically within the urban fabric. Benthamplain exemplifies Rotterdam's broader strategy, using adaptive zoning and multifunctional landscape design to reduce flood risks while delivering high-quality public space. It is widely regarded as a benchmark for cities seeking to link resilience, livability, and community-centered design in a single integrated intervention. Singapore offers one of the world's most advanced examples of climate-responsive zoning through its performance-based approach to urban greenery and environmental design. Unlike traditional zoning systems that focus on land use categories, Singapore requires developers to meet quantifiable environmental targets, most notably through the LUSH program and the green plot ratio. These instruments ensure that every new development contributes meaningfully to the city's ecological network, whether through vertical green facades, sky terraces, or expansive rooftop gardens. What makes Singapore exceptional is the integration of zoning with microclimate and biodiversity modeling. Planning decisions are supported by detailed simulations of solar exposure, shading patterns, wind flow, and habitat connectivity, enabling a finely tuned relationship between built form and environmental performance. This approach is supported by strong institutional coordination across the Urban Redevelopment Authority, the National Parks Board, and the Building and Construction Authority. The results are measurable: reductions in local air temperatures, improved thermal comfort, and significant increases in urban biodiversity. Singapore's model demonstrates how performance-based zoning can transform highly dense urban environments into ecologically productive and climate-adaptive landscapes, setting a global benchmark for resilient city-making. Beyond its environmental performance, Singapore's zoning framework illustrates how regulatory instruments can actively shape market behavior and long-term urban form. Performance-based requirements such as the green plot ratio are embedded directly into the development control process, ensuring that ecological outcomes are not optional enhancements but baseline expectations. These requirements are reinforced through incentives, including additional floor area allowances and streamlined approvals for projects that exceed minimum environmental standards. Crucially, Singapore's approach is supported by policy continuity and regular regulatory updates, allowing zoning standards to evolve alongside climate projections, technological innovation, and ecological research. While the city's strong institutional capacity is context-specific, the underlying principles are measurable performance criteria, data-informed decision-making, and cross-agency coordination offer transferable lessons for other dense cities seeking to reconcile development pressure with climate resilience and ecological productivity. New York City represents a critical case of how large metropolitan regions can transform their zoning systems after experiencing significant climate impacts. Hurricane Sandy in 2012 exposed widespread vulnerabilities in the city's coastal neighborhoods, particularly in low-lying communities that lacked adequate flood protection. In response, the city launched the Resilient Neighborhoods Initiative, which engaged residents directly in designing zoning strategies tailored to each district's unique exposure and social conditions. Central to New York's approach were the zoning text amendments that allowed buildings in flood zones to elevate their ground floors, incorporate flood-proof materials, and redesign mechanical systems above projected flood levels. These amendments helped remove regulatory barriers that had previously limited resilient construction. The city also created special coastal risk districts, which introduced more restrictive development standards while offering flexibility for adaptive design. Importantly, New York embedded equity considerations into its resilience planning, ensuring that vulnerable populations received targeted support. Combined with nature-based flood protection measures and long-term frameworks such as 1 NYC 2050, the city now stands as a global example of how zoning, community engagement, and legal adaptability can intersect to strengthen urban resilience in the face of accelerating climate risks. Tokyo is one of the most densely populated metropolitan regions in the world. At the same time, it is located in one of the most seismically active areas on Earth. This combination makes Tokyo a very important example for understanding how high-density cities can remain safe, resilient, and functional under strong earthquake risk. Instead of reducing urban density, Tokyo focuses on strengthening design, planning, and monitoring systems so that people can continue to live and work in compact conditions without facing excessive danger. Seismic planning and building safety. One of the most critical features of Tokyo's urban resilience is its strong building code system. After major historical earthquakes, the city introduced advanced seismic design standards. Today, seismic retrofitting is mandatory for vulnerable buildings, especially older reinforced masonry structures and critical facilities such as schools, hospitals, train stations, and emergency centers. Structural safety is not seen as a one-time action. It is a continuous process. Regular vulnerability assessments, mandatory inspections, long-term retrofitting programs, incentives for upgrading private buildings. This means that high density is not avoided, but made safer through engineering, monitoring, and regulatory enforcement. Street networks and public space as evacuation infrastructure. Tokyo does not only think about building safety, it also considers urban design and mobility during emergencies. Dense districts may experience congestion, so the street network is designed to support multiple evacuation corridors. Wide boulevards, open parks, riverfronts, and public plazas are planned as assembly areas, emergency routes, and temporary shelter spaces. The coupling of public space and the street network is essential. Large parks and well-connected corridors reduce panic and crowding, allow emergency vehicles to move efficiently, provide safe gathering spaces for large populations, act as fire breaks during post-earthquake fires. In other words, compactness does not mean narrowness. Tokyo shows that dense cities can remain highly accessible if public space networks are integrated into the planning from the beginning. Vertical density with safety principles. Tokyo actively promotes vertical development. Instead of allowing uncontrolled horizontal sprawl, the city supports compact, mixed-use, and transit-oriented districts. Vertical density allows the city to use land more efficiently, reduce energy and transportation needs, protect suburban ecological areas, concentrate services in well-served hubs. Vertical growth is not a risk by itself. It becomes safe when supported by high seismic standards, redundant structural systems, backup utilities, well-organized evacuation planning within tall buildings. Tokyo demonstrates that the goal is not to reduce density, but to design density with safety in mind. Digital monitoring and real-time coordination. Tokyo also uses advanced digital technologies for real-time risk monitoring. The city operates one of the world's most sophisticated IoT and telecommunication systems for earthquakes. These systems automatically collect data on seismic intensity, infrastructure performance, mobility patterns on public transit, emergency route capacity. Real-time monitoring allows authorities to send early earthquake alerts to mobile devices, slow down or stop trains instantly, coordinate evacuations, manage crowd movements, activate emergency response centers. Digital data increases efficiency and reduces casualties, especially in dense environments where every minute is critical. Why Tokyo matters for urban density and risk mitigation. Tokyo is a valuable case study because it clearly shows that urban density does not necessarily increase risk. If density is supported by strong building codes, spatial planning, evacuation networks, and digital monitoring, it can function safely even under major natural hazards. The Tokyo model teaches us an important lesson. Instead of reducing density to avoid danger, cities can design density to become safer, more resilient, and more adaptive. This approach is different from the traditional idea that risk can only be reduced by decentralizing population. Tokyo demonstrates the opposite. Compactness, when planned intelligently, can actually improve safety, reduce response time, strengthen infrastructure management, and provide better access to emergency services. Lecture takeaways for students. High-density cities are not automatically risky. Risk depends on planning, regulation, monitoring, and community preparedness. Seismic safety is both structural and spatial. Resilient buildings must be supported by resilient street networks and public spaces. Vertical development can be safe if building standards, evacuation design, and inspection systems are strong. Real-time digital monitoring increases situational awareness and enables faster and more accurate emergency response. Tokyo is not reducing density, instead, it transforms compactness into a safety advantage. Copenhagen is a dense European city that has increasingly faced the risk of extreme rainfall events, also known as cloudbursts. Climate change has intensified short-duration, high-intensity storms that overwhelm traditional drainage systems, leading to surface flooding, infrastructure damage, and disruptions to daily urban life. Because Copenhagen has a compact urban fabric with limited space for large-scale gray infrastructure, conventional flood control solutions alone were no longer sufficient. In response, the city developed an innovative cloudburst management strategy that rethinks how water moves through dense urban areas. Rather than treating stormwater as a problem to be hidden underground, Copenhagen began to design with water, integrating flood management directly into streets, public spaces, and open areas. One of the key principles of this approach is the redesign of streets as controlled water corridors. During extreme rainfall, selected streets are intentionally shaped to guide excess water safely through the city toward parks, canals, or retention areas. Curbs, surface slopes, and materials are carefully designed so that water follows predetermined paths, minimizing damage to buildings and critical infrastructure. Under normal conditions, these streets function as everyday public spaces, supporting mobility and social activity. Another essential component is the integration of blue-green infrastructure. Green spaces, urban parks, permeable surfaces, and vegetated areas are designed to temporarily store, slow down, or absorb rainwater. These elements reduce pressure on drainage systems while also providing ecological benefits such as cooling, biodiversity support, and improved urban livability. Blue infrastructure elements, such as canals, ponds, and water plazas, work together with green systems to manage stormwater across multiple scales. Importantly, public spaces are redefined as part of the city's risk infrastructure. Parks, plazas, and open spaces are no longer seen only as recreational areas, but also as temporary water retention zones during heavy rainfall. This multifunctional use of space is particularly important in dense cities, where land is scarce and every square meter must serve multiple purposes. Concepcion is a medium to high-density city in Chile that was severely affected by the 2010 earthquake and subsequent tsunami. The disaster caused extensive physical damage, displaced large numbers of residents, and exposed structural, spatial, and social vulnerabilities within the urban system. Rather than focusing solely on rebuilding damaged structures, Chile adopted a post-disaster urban regeneration approach that combined reconstruction with long-term risk mitigation and adaptation. This strategy reflects the principles of adaptive urbanism, which emphasize learning from disaster impacts and using reconstruction as an opportunity to improve urban safety, resilience, and spatial organization. In Concepcion, post-disaster planning was not treated as a temporary response, but as a long-term transformation process. One of the key priorities was to integrate risk reduction directly into reconstruction decisions. New development followed stronger seismic building codes, ensuring that rebuilt structures could better withstand future earthquakes. At the same time, land use decisions were revised to reduce exposure, particularly in areas vulnerable to tsunami and coastal flooding. A central component of the regeneration strategy was the creation of ecological buffer zones and wetland restoration. Instead of rebuilding densely in high-risk coastal or low-lying areas, these zones were redesigned as open spaces, parks, and restored wetlands. These ecological buffers serve multiple functions. They reduce tsunami and flood impacts, provide environmental benefits, and create safer separation between urban development and hazard-prone areas. Housing reconstruction also played a critical role. Safer housing areas were developed for displaced communities, with attention to both structural safety and access to services. This approach aimed to reduce social vulnerability by avoiding the relocation of low-income populations to unsafe or peripheral locations. Housing quality, connectivity, and accessibility were considered essential components of resilience. Importantly, community participation was embedded in the planning and regeneration process. Residents were involved in decision-making through consultations, workshops, and local planning initiatives. This participatory approach helped planners understand local needs, mobility patterns, and social networks, while also strengthening trust and community ownership of the recovery process. This example highlights several key lessons. Post-disaster regeneration can reduce future risk if reconstruction is guided by adaptive planning principles. Medium and high-density cities can remain compact while becoming safer through ecological buffers and revised land use strategies. Social factors, such as housing security and community participation, are essential to effective risk mitigation. Adaptive urbanism transforms disasters into opportunities for learning and long-term urban improvement. Overall, Concepcion illustrates how rebuilding after disaster can become a proactive strategy for creating safer, more resilient, and more inclusive urban environments, rather than simply restoring pre-disaster conditions.